Hello. Hello, welcome to another edition of Spotlight the Science, where we get to meet the amazing ADA-funded researchers and learn more about the exciting work that they're doing to prevent and cure diabetes and improve the lives of all people affected by diabetes. So my name is Marlon Pragnell, and I'm the VP of Research and Science at the American Diabetes Association. And today, we have the privilege of speaking with Dr. Sumita Pennathur. Dr. Pennathur is a professor of mechanical engineering at the University of California, Santa Barbara. She holds a BS and an MS in aerospace engineering at MIT and has a PhD in mechanical engineering from Stanford University. She has many awards, patents, is a noted speaker, and also is the recipient, a past recipient of the prestigious ADA Pathway Award. Welcome, Dr. Pennathur.
Thank you so much. Thank you.
So you're working on the cutting edge of diabetes technology. Uh, Tell me, you have your education, your bachelor's and master's in space engineering. How did you get into diabetes research?
Oh, that's a great question. So I started at MIT Stanford. I'm a professor at UCSB. And as a professor of mechanical engineering, we strive towards making new innovations that could actually help people. The work that I was doing has always been in the bioanalytical space, so really trying to figure out how we can further the technology of biology. And with to that end, I started a couple companies. And when I was trying to figure out, hey, trying to figure out what do I want, what do I want to tackle? What is it that I want to tackle? I'm just working on little biology things. I want to tackle a real disease. What should it be? And when I was trying to go through that, my 4-year-old at the time got diagnosed with type 1. So it was almost like, every cloud has a silver lining. It was like, I have to do this, right? It was a calling. She got diagnosed and I had to go through the trials and tribulations of the technologies today. And I'm like, I can improve this. This is why I became a mechanical engineering professor, because I can make things that are going to help her. So
Wow.
it was a simple way to get into.
So you had, in a sense, a front seat on the
Yes.
needs of people with type 1 diabetes and where what's available, what are the therapies, which are amazing advancements and so on that are available in recent years and so on, but maybe also some of the gaps, the needs,
Mhm.
what people with type 1 diabetes would really like, obviously a cure, but on the way
Mhm.
to a cure, better technologies. Can you kind of tell us a bit about kind of the areas that you've thought about?
Oh yeah. So again, I'm a mechanical engineer. I'm not going to rethink biology to try to come up with a cure. What I can do is build devices that I believe will help people with all sorts of diabetes, but specifically type 1. People with type 1 have to think about it every single day. It's we all know it's a chronic disease and it's difficult. And I, you know, cry for my daughter almost every day. She has a lot she's going through every day, but we can help. So there has been continuous glucose monitors that are attached to your body that help read your sugar levels at all times. There's insulin pumps that help give you insulin all the times. The problem is these have been out for 10, 20 years. They still aren't there yet, right? They have lags. In fact, I was just reading a paper that showed that from 2012 to 2018, people who were wearing CGMs and pumps didn't actually have better outcomes, like their HbA1c, their level of control. In some cases were worse, especially for the younger people. And the hypothesis is because when you have a device that tells you your sugar all the time, if you're high, you end up taking too much insulin, then you go too low, then you take sugar, you go too high. So it's like a roller coaster. And that's not what we want. We made these devices to help people, to make sure people knew what they were doing, not create roller coasters. So I think that there's a huge room for improvement in both the monitoring and pump space. As you know, we've tried to make an artificial pancreas for many, many years. One of the problems with making an artificial pancreas is that the devices right now are delayed, right? If you wear a continuous glucose monitor on your body, there's a 15-minute delay with your blood. And people are trying to work on that, but there's still a delay. And that makes this roller coaster, right? So one of the things I'm doing, for example, is dermal sensing. So we want to sense in the dermal space, which is closer to blood. Now we don't have the delay. Now we can actually make an artificial pancreas. Similar, if you give insulin in the dermal space, it's faster. And there's all sorts of things that we can do to make pumps better. Pumps, they only last 3 days right now. The reason they only last 3 days
Mhm.
is there's many reasons, but one of the reasons is because your site, right? You're putting insulin in one place over and over and over again. Your body can't handle it. Insulin has um, metacresol and phenol. Those things
Yeah.
are essentially poison, but they're used to help stabilize the insulin. So little
Yeah.
amounts are okay, right?
Yeah.
But theoretically, if we can get rid of the phenol metacresol before it goes in the body, we keep it to keep the insulin stable, but then we get rid of it,
Mm.
we might help the body. And so I'm working on things like that. There's all these little, we can go into it in more detail, but all these
Yeah.
little things that we can do to improve
Yeah.
the standard of care.
Yeah, it's interesting how you say the delay because I mean, people with type 1 diabetes have to give themselves insulin prior to a meal, planning,
Mhm.
and so
Mhm.
and these delays that you have with like when you do injection and so on. Same thing with the closed loop and
Yep.
the AID artificial pancreas systems where there is a delay in there, and so um, uh, so you mentioned the dermal space. So I know the infusion sets go a little bit deeper, right?
Mhm.
So where's the acceleration there from both the sensing side and also from the delivery side? How does it
Delivery.
get faster?
That's a really great question. So your skin, you have an epidermis, you have a dermis, and then you have subcutaneous tissue. It turns out that, and this is a little bit counterintuitive, but in the dermis, you have a bunch of blood vessels that in the sub-Q is used up, but in the dermis it's there, which means that it actually matches what your blood. It's closer in terms of kinetics to your blood, right? So your subcutaneous is actually a little bit delayed because it's the blood vessels don't get there fast enough. There's not as many, and as they go, you have to wait. You have to wait for things to diffuse from the blood vessel. And the dermis, it's all there, right? And so the kinetics are faster, which means that
Mm.
when you're sensing or you're delivering, things will, sensing especially, you're going to sense it faster because it's matching what your blood does, right?
Right,
Uh,
right.
and
So
it
you
gets
have
into.
then because I know the current CGMs don't really report immediate blood
Mhm.
glucose levels. They report interstitial fluid within the cells, and so there's a delay there. So what you're saying is that if you sample from a slightly different area in the skin,
Mhm.
you get close to the blood and you get a blood measurement,
We
right? So
get
that's a
yeah,
lot
we get
faster.
something. Exactly. We get something that is closer to what your blood is, much, much closer to what your blood is. We've noticed
Mhm.
between 0 and 2 minute delays versus 10 to 15-minute delays.
Yeah.
So
So you
it's,
so So you get then faster sensing and then faster delivery too, then, right? Because you're getting access
yes.
to the blood, right?
Yeah,
So the
that's the
focus,
hypothesis.
that's I see. So there's the acceleration. But you mentioned a bit of Cresol and so
Mhm.
can you talk a bit more about that?
Sure.
Mm.
So I just finished telling you about the delay for the dermis. That's one
Yeah.
innovation. Right?
Mhm.
The other innovation is, okay, let's put a pump on your body. When you put a pump on your body, um, you're putting insulin in your body at all times. So you're continuously pumping insulin to your body in one site, right? This is not the same pen injections. You put it all over, different times everywhere. But if you have a pump that's in one place, you're putting insulin in your body in that one place the whole time. And nobody has been able to make a pump that lasts more than 3 days. Why not? We don't know why not. But most of the time, it's because after 3 days, you're just not as it's not as efficient, right? And there's lots of hypotheses for these. One of the hypotheses is that your skin is just getting too much insulin, right? It's trying to reject it. And why would it reject it? Well, one of the hypotheses for being rejected is because metacresol and phenol are in insulin, which is essentially poison. They're there to stabilize the insulin. And they're very, very low quantities, low enough that it passes the FDA and it can actually get through. But they they sort of uh, may cause your skin to not act properly. So one of the things that we're working on is, hey, in the pump itself, like as it's going through the tube into the pump, like in the infusion set, why don't we just take out the metacresol and phenol? How do we take it out? We can apply a little electric field, right? And electro-oxidize it. So yeah, people have shown that, hey, you put a little carbon electrode around the infusion set and you zap it, you can actually get rid of the phenol and metacresol. Very, very cool. Why isn't it in pumps right now? The reason it's not in pumps right now is because phenol and metacresol, as you zap it, it coats the electrode, right? And so you only can zap a little bit amount, right? Because once it coats the electrode, that's it, you're done.
Stops
So you
working.
can't actually get a lot out. So the innovation that we did at UCSB, the paper we just published, and what I'll be talking about at the ADA, is we figured out a way to mimic the body. We put a sort of gel layer on top of that electrode so that we can zap a lot better, right? And so now the metacresol and phenol, we can actually hold more and more and more, and the electrodes still work good. So electrooxidation. So we show that, hey, if we manipulate the electrode like this, we can actually get all the phenol metacresol out of the insulin, and we're good.
Well, seems like that we're talking about infusion sets and so on, also to the intradermal space, but it seems like it would be valuable even in today's infusion sets, I would imagine, because
Yeah.
the 3 days and to extend it longer. Are you doing any studies or experiments or animal studies or clinical studies to see how it may extend infusion set life?
That's a great question. We're trying, and we're hoping to work with Tandem or anyone here who's interested. We're trying to continue that project, and I think the data that we show is very promising. So we're hoping that we can work with a pump company and actually implement it now.
Your work, I've seen in your work, you mentioned microneedle approach. So tell us more about that and potential. I know it's a very early new area, but very exciting. Tell us more about your experiences and where it's heading.
Yeah, that's a good question. So microneedles are a way to get things in the dermis, right? People have been using it for a while. They've been using it for delivery of drugs. It is extremely difficult to get microneedles to sense, right? Because it's very hard to keep them in the skin. The body wants to reject needles, right? The body wants to reject hard things. So if you're trying to use microneedles to sense, you have to be clever on how you do it, right? You have to not do something hard that's going to, make the skin push it out. You have to be clever about how you're actually, getting it in that dermal space and not having it push out. And unfortunately, I can't tell you more about that because we did spin off a company that figured out a way to do it. And so we have to keep that a little bit secret.
Awesome. Fascinating. So we talk about intradermal space, the dermal space and sensing and delivery. And so how about, when we look at today's pumps and sensors, we're seeing a person putting a CGM component on one part of the body, maybe having a pump in the pocket, or and then having an infusion set to another part of your body. What's the future hold in terms of making things smaller and like an all-in-one kind of single location, just put it on and then use that? I assume that's some of the kind of areas that you're kind of targeting as well, the kind of miniaturization to make life much more, just kind of making these less obvious and more less intrusive for people.
Yep, that's the goal, right? A peel and stick. I just take something out of a package, peel it off, stick it on your body, and it does everything. It acts as the pancreas. That's what we want. That's what we're working towards. I think the dermal sensing and delivery is really going to help. People, not me, have shown that, one of the worries was, hey, we can't sense and deliver in the same place, right? Because that's going to mess up the readings. But people have shown, you can have something a little bit, 2 centimeters away from the other thing. So we could possibly do a peel and stick where there's a sensor one part and a delivery on the other part. So, it's slow and steady, but definitely I think it is possible to make an artificial pancreas that is small, compact, has the sensor and the pump in the same place. We're far away from it, but it is achievable. And I'm striving to achieve that.
Yeah. So why not? I mean, when you say it has to be a little further apart because they
Yeah,
would affect each other, what's happening there? Why would that happen?
because if you're trying to measure your glucose levels, but you're putting insulin in the exact place you're measuring your
Dilute it?
glucose levels, yeah,
Ah,
it could
sure.
affect what
Makes
you're
sense.
eating, right? So, yeah.
Makes sense. So you are, an accomplished researcher, multiple patents. You mentioned also your company. I mean,
Hmm.
that's a whole another dimension of expertise and learning and opportunities. Tell us a bit more about that, and I imagine it must be very exciting and a new area of kind of trying to take this research and translate it to actually get it to people.
Yeah, I think that's every professor's dream, right? The research that they do can actually be translated and into something that helps society and helps the world. Usually, professors need 20 years before that happens. Mechanical engineering professors, it's a little bit better because we're doing something more practical. And given my daughter's situation, it was like I have to push. I want to push as fast and furious as I can. And the way that we were able to do that is I'm working 100% on the pump at UCSB, working on the phenol metacresol work. We're trying to make better pumps, smaller pumps, everything that you're talking about. And the continuous glucose monitor, we know we can fix it, if we can do dermal sensing. So we spun off a company named after my daughter, Lakshmi Therapeutic Devices, to actually build a CGM. So they're very separate. So they do the CGM at the company, I do the pump at university, and I'm trying to put it all together.
Awesome.
Yeah, and I think that it is extremely different. The company is 100% focused on getting a product to market. Very, very different than the research and development we're doing at the university, where we're just trying to look at the problems and solve the problems, and just take that first step and make innovations. The company is just focused on making that product that's going to help people.
Right, on the CGM aspect. So,
Yeah.
so making a pump smaller. I mean, we look at the current pumps; and they're large. I mean, I know
Mhm.
there's one that you can wear, a pump you can actually wear on your body. But I noticed in some reading about some of the work, you're working on pumps that have like no mechanical parts in them.
I
That's
am. Yeah.
fascinating. How do you do that? I mean, there's no mechanics there. How do you move? How do you get to pump things without any kind of mechanical
That,
part?
that's a great question. So yes, the what I do in my lab is electrokinetics. So what does that mean? It means I drive fluid with electric fields. So what does that mean? It means salt water. Salt water is charged. There's charges, there's plus and minus charges. When I apply an electric field, the charges move. If we do it in a macro sense, if I do it like in this glass of water, I apply an electric field, we will shock ourselves, and there's too many volts and we'll electrocute ourselves. But at the nanoscale and the micro scale, when you're dealing with tiny, tiny channels, you don't electrocute yourself because the current is small, right? It's a very small current. So we can actually move fluids around using electric fields. So there's no mechanical parts, there's no pumps and valves, but there's electric fields. So we're actually putting electricity, we're using an electric force as opposed to a traditional mechanical pressure force. And that has been my field of study for 20 years. I've really worked on understanding what's going on at that scale and exploiting that to move fluids and to make a pump is what I'm doing. Trying to do very innovative stuff here, right?
Mhm.
And there's ways that we can manipulate the fluids and manipulate the geometry to actually make fluids create pressure, and that pressure will move a membrane, and that membrane will move a fluid.
Wow. And then that obviously then will help that is enable more miniaturization as well, I imagine, uh,
Of
as
course,
opposed
yeah.
to kind of much
Yeah.
larger pumps and so on. So
Yeah, because pumps are large because they need batteries, which again, electrokinetics, we use very little current, so the battery will go smaller. And they need valves and mechanical parts to push. Doing stuff at the microfluidic scale can make things much smaller.
Wow. Would that then also a smaller, could there be more economies and so on where you could actually have more of like a disposable pump, for example, as opposed to these highly mechanized large pumps and so, or is that something that is, these will be rather still somewhat kind of costly to produce.
I am hoping it's disposable, right? Insulet right now has a 3-day disposable pump, and I think their parts are much more expensive than what we could possibly do with electrokinetics. So yes, again, the goal is to have a all-in-one pump with a
Yeah,
CGM
yeah,
and
yeah. It's absolutely fascinating, the actual progress in the last years in CGM technology, pump technology, bringing them together. I mean, it's transformed people's lives, but what's clear is there's so many gaps and so much more opportunity there, and it's great that you're working right on the cutting edge of all the future opportunities around kind of uh, pumps, sensors, and how to bring them together to create much more smaller, more effective, more faster closed loop. So really appreciate all the work you're doing, and it's been great talking with you and chatting and learning about your work. Thanks so
thank
much.
you. Thank you. Thanks a lot.
Good. All the
Great.
best. Thank you so much.
All right. Thank you.
Good.